Hello, everyone, and welcome to today's session of InfluxDB IOx Tech Talks. My name is Caitlin Croft, and I'm super excited to have you all here today. First, I'm going to give our friends a couple of minutes to join, but while we wait, just giving everyone a couple of friendly reminders. This session is being recorded and will be made available later today on YouTube. And I will also make sure that the slides are made available so you can review them as well. Please feel free to post any questions or comments you may have for any of the speakers in the chat or the Q&A box, which can both be found at the bottom of the Zoom panel. I will be monitoring both and will make sure to have the panelists answer your questions at the end of the session. Just a couple of friendly reminders. We have these Tech Talks every month, and we also have other webinars and we throughout the month, as well as our virtual time series meetup. The next virtual time series meetup is going to be in April, and it will be about monitoring your internet service provider with InfluxDB. Certainly something that I'm sure a lot of us are interested in as we are all stuck at home. Influx Days is coming up. Influx Days EMEA 2021 is going to be held in May. We're super excited to see everyone. Obviously, we can't wait to see everyone in person, but it's still fun getting to hang out with everyone online. In addition to the conference part of Influx Days, we also have a couple of different trainings. We will have the popular Flux training, which is coming back, and also the Telegraph training, which was super popular last year. So there are limited seats for both of those trainings, so be sure to check out the Influx Days website and register for them if you're interested. It's always fun. I'm always amazed at how interactive and social the InfluxDB community is. And even with Influx Days being virtual last year, it was so much fun. We had trivia and a happy hour and a mixology lesson. And amazingly, someone from InfluxData didn't actually win trivia, even though a lot of the questions were about us. Apparently, their community knows us better than we do. So it's going to be a lot of fun this year. So hope to see you all there. Hope to see you at any of our other future events, whether it's the meetups or webinars or these monthly tech talks. All right, without further ado, I'm going to hand things off to Paul Dix. And once again, this session is being recorded and will be available later today. Off to you, Paul.
All right, thanks, Caitlin. Give me a thumbs up if you can hear me well.
You sound great.
All right, great. Thanks for dropping in, everybody. I'm just going to give a quick update on the project status before Andrew gets into the really interesting part of the content. So InfluxDB IOx, just as a reminder, is a new columnar time series database. It's basically the future core of InfluxDB. It's written in Rust. It uses Apache Arrow, and it uses object store for persistence. So on to the update. So first, a little bit about the API. Some of this is going to be a review because we had mentioned it last month, but we have progress here as well. Obviously, you can ingest the InfluxDB 2.x line protocol with IOx. This is part of our efforts to provide compatibility. So there's a seamless move from previous versions of InfluxDB to versions of InfluxDB that use IOx as the storage piece. The HTTP interface for querying data now supports JSON and CSV and print outputs. So basically you can send it a SQL query and it will give you data back. The interfaces for querying over InfluxQL and Flux also continue to move along. Basically those are a separate API layer with the InfluxQL and Flux pieces, which are basically Go processes that connect to it. Arrow Flight is there now, so you can actually connect any Apache Arrow client that can speak client, connect it to IOx and actually issue a query, a SQL query, and get data back. that's super easy in first-class Arrow environments like Python, Java, C++, R, and a bunch of others. So last month we announced that basically the API interfaces in IOx are going to be one part HTTP, basically for reading and writing data, one part of writing data, and then the other part, which is basically a gRPC API for doing management, for doing data replication, for doing bulk data movement. So we've actually started the process of implementing the first parts of that gRPC API and a command line interface for it. So whatever you can do through the gRPC API, you're also going to be able to do via command line that executes against the host. So you can create databases. We've started work to define replication and sharding. And we've added to the README instructions for how to use the utility grp curl to interact with this gRPC API. And we're also going to be using gRPC health as a health check on the gRPC side of things. So on the query side of things, one of the great things is queries now work across the mutable buffer and the read buffer. So as a reminder, the mutable buffer is the area in the database that basically is hot for writes and receives data as it's written in. So it's optimized for that. The read buffer is the part of the database that's optimized for providing both in-memory compression and execution speed on the queries. So now DataFusion on top can query data that originates from both the mutable buffer and the read buffer, which is basically the first part of us adding in all the bits to have an automatic data lifecycle between data landing hot for writes, getting moved off to being fast for queries, and eventually getting moved off for persistence and object store, both in bulk and reading out data as well. So one of the bets we made early on with this project was that we wanted to base things on Apache Arrow, but we also made a bet on a project called DataFusion, which is basically a SQL execution engine and parser and a bunch of other stuff in Apache Arrow that's written in Rust. And one of the reasons we wanted to do that was because we wanted a way to collaborate on this functionality with other people in the community that may or may not even be using IOx. We figure there are going to be many people using Arrow and many more people using Rust over the coming years. And we wanted to contribute back to that to help move it along, but also benefit from community interaction and improvements to it. And the great thing is we're seeing that as we go along, even in these early stages. So some of the features that have been introduced, a whole set of Postgres string functions. I guess that's one of the other things that may have happened between the last update and now, which is the DataFusion project has decided to standardize on the Postgres flavor of SQL as the SQL that they'll be using. So what that means is the flavor of SQL that IOx will use as a first-class citizen is the Postgres flavor. Support for extracting data, say extracting hour from a date column. There's also been some interesting work on performance. So optimize function implementation for scalar values and columns, improve join indices, support for more advanced statistics and expression rewriting. And this we see is just going to continue going. So now here's a set of updates basically on the command line interface, specifying configuration, and basically the other category. So you now can write line protocol from a file. You can execute SQL queries from the command line rather than using curl or whatever. You can just specify it via the CLI. You can create a database. You can specify now on the startup process what the object store parameters are, and that's kind of normalized between the different object stores that we support, GCP, Azure, AWS. And we've started to begin work on an implementation to do meaningful background task tracking. So background tasks could be long-running queries, but it could also be movement of data from memory over to object storage or retrieving data, anything that can happen in the background that may take a while to run where you'd want to be able to track it. So we're going to have a system for tracking all of these things And you'll be able to get information about those tasks that are running in the background, both via the CLI and the gRPC API. So the last bit is probably what people are very interested in, which is what does the path to creating open source builds look like? Now, last month, I said we were hoping to get builds out by the end of this month. And the truth is, we've gone through over the last couple of weeks and we've done a bit more project planning. And we realized that we're not going to be able to put something out there by the end of this month that we want people to meaningfully test. If people want to collaborate with us on the code and really dig in there, that's great. And we fully accept that. But we don't think it'll be ready at that point. We want something that we put out where it's useful and interesting for people to test with larger data sets, to see how the querying works, to see how the data movement works from object storage, and to see how data movement works across multiple IOx servers. So that's kind of our bar for what we're saying we want to put out there with the open source builds. So how do we get there? So first and foremost, we want to dog food IOx as a project. We want to dog food it for our own monitoring purposes. So we run InfluxDB Cloud, a separate installation to monitor all the clusters of InfluxDB Cloud that we own and operate. So we want to be able to handle this, the write ingest of this in memory first, which is about 1+ million values per second. There's a bit of debate about where in the million value range it is, but it's definitely above 1 million. And whatever that is going to be at least 2x for replicating that data. So we want to have that in memory. We want to have basic proxied and distributed query support, because at that scale, we're going to be splitting the write load across multiple servers, and we need to be able to query that and combine it at read time. We need tools and configuration to talk about the lifecycle of data writing, data landing in the mutable buffer, hop to writes, and then off to the read buffer, so that when we actually pull up our dashboards and query this thing, it's going to be fast and performant. The next bit is getting to the persistent side. Now, actually, all of these bits, 1 through 3, we're going to be doing that, and we're actually going to be using that in production alongside our existing storage system. But obviously, to take over our storage system, we need to add the persistence part. So the first part of that is buffering the write-ahead log in memory and persisting it off to object storage. We need to be able to support subscriptions, which is how IOx servers pull data from each other, both in real time and periodically in batch. We obviously need to support Parquet persistence for, it's not enough just to persist the wall. It would take too long to replay the wall every single time. So we need to have the optimized compressed files out there so that we can persist them and have them available so that we can do recovery at a later stage, both from object storage and from other IOx servers. So once we've gotten through this set, this is basically a meaningful set for us to be running this exclusively for our production use case for our own monitoring, which is a pretty interesting milestone for us. So after we've done that, we've kind of proven it out enough where we feel like, okay, there's a meaningful production workload we support. Now we need to start getting all the bits ready so that the single server pieces are there, right? In our production use case, we're going to be running this across multiple servers in an interesting configuration, which we will talk about. But for users to play with IOx out in the community, they're going to want to be able to do it just on their laptop, on a single server. And we need to give people the tools to specify a configuration that will have it just running in a steady state. And then we'll need a command line interface, which obviously we're building along the way for all that configuration. And then finally, we need documentation for everything so people understand how to use the thing and how to test it and what kind of feedback we're looking for. So that's the path. Taking up more time than I meant to, so I want to hand off to Andrew right away, but I'll stick around and we can do Q&A after Andrew's talk. Thank you.
Well, all right, can you see my screen?
Looks great.
Yep.
All good. All right. Thanks, Paul. Thank you very much. Yeah, so like Paul, what I'm going to do right now is I'm going to talk a little bit more about what Paul was describing, the DataFusion engine, and I'm going to dive into slides and I'm going to talk about what that is. So hopefully you'll find it interesting. So a little bit of background on myself. I basically had two past lives that are relevant maybe for here. First, I spent quite a few years working on the query optimizer on a database called Vertica, and I worked at Oracle on the database server prior to that, and some other low-level sort of systems programming stuff. And then I also, the last couple of years, have been working as sort of the chief architect of VP of engineering roles, and I'm super psyched to get back to the query optimizer stuff. So I've been deep down in the guts helping work on the IOx query engine, and I wanted to tell you more about what was going on with DataFusion. So I don't really know why you all came to this talk, or like basically what the background is. So I have effectively two thrusts of this talk. The first is to try to explain, like it's half sales pitch for DataFusion, explain what it is and how, like at a high level, why you use it, where it fits in. And then the second half is really like down in the guts, if you are interested in contributing to DataFusion, to have like a high level understanding of what some of the major structures are and how it operates. So, hopefully you'll find at least one of those halves interesting. And so without further ado, I'll start at the super high level. So, we were talking about query engine and DataFusion and SQL and stuff, like just to set the base of where things start, what is a query engine used for? At the end, like this is back even starting in the 60s or 70s, right? Like you had data somewhere on computer systems and you had users who wanted to access them. And at first only people who could program could, actually write programs could take advantage of that. Then over time, it's clear that there's a lot more people who want to have access to the data on the computer than can actually write the programs. So you ended up with a whole bunch of sort of, effectively what happened was query engines help bridge that gap. So typically users interact these days even with visual UIs or possibly with the command line. Those will then issue queries, not necessarily programs directly, but some sort of higher level description of the data they want. And then the query engine is typically a piece that maps their request of what they want to actually getting it off wherever it's stored. Super high level. Oh yeah, and so Paul mentioned SQL. Query engine in general is a general concept, but SQL is more or less the default de facto standard for doing this, despite everyone who hates it. It's like the least worst of all possible query languages. So DataFusion, actually, I'm going to spend the whole rest of the time talking about databases and how it works in the database system. I think interestingly, DataFusion also has a bunch of other use cases that I've seen people start to use for, and in particular around data engineering, which right now you still more or less end up writing custom programs to do your data manipulations. And I think what's happening is a bunch of interesting data, classic database internals sort of technology is making its way up the stack. So for both ETL and data science. So while I'm going to talk entirely about how this is related to databases, it's actually interesting that I think it's actually going to show up and be used in these higher levels as well over time. So it's even better, right? We're connecting to even a bigger of an ecosystem, not just people who are doing databases. And as Paul said, actually, IOx is just one of several existing database systems that have started to use DataFusion, and I think that's a pretty good indication that it's actually living up to some of its goals. So why DataFusion? This is the marketing part I was talking about, right? So basically, the goal of DataFusion is you have a high performance query engine written in Rust. Not only that, it's able to leverage Arrow to take advantage of all that performance. You also have the ability to, because it's part of the Arrow ecosystem, it's not part of Arrow. We'll talk about that briefly in a second, but because it's part of that sort of project and uses that format in the libraries, I think it turns out that it ends up being super easy to connect. So if you've got data in Arrow and you want to write queries against it, DataFusion can help. Because it's written in Rust, and actually from the get-go, Andy Grove designed it to be able to be extensible. You can basically plug in whatever you want, wherever you want. So it's very sort of whatever your use case is, it's easy to extend to make sure that it matches. It's totally written in Rust. We have a whole bunch of extensive unit tests. So I think like the goal here, my real goal is to make this thing, if you want to write something that writes SQL, not connects to SQL database and runs SQL, right, but actually gets a SQL query and lets people ask about data stored in your system using SQL, or the data frame API, which I'll talk about, DataFusion should be it, right? So I also have to talk about what DataFusion is not, right? So you might think it's a database, or like what's the difference between a query engine and a database? So I'm not going to read all this, but databases come with typically a whole raft of features that range the gamut from actually storing the data to access control to making sure it coordinates across a bunch of different machines and who's in the cluster, and maybe provide JDBC connectivity. Like there's a whole set of features you want in addition to the actual sort of core querying. Right? So DataFusion is designed to be this piece. And then if you want to build a database, very much like IOx, right? You might imagine this is like some high level feature or component list of IOx, which is true, right? We're able to use the query engine, and then we're going to go customize these other subsystems for our specific time series use cases. But we'll be able to take advantage a lot of what DataFusion does. So what is DataFusion? You can read about this. I'm not going to read the slides, but I think the high level is kind of interesting. DataFusion follows a pretty classic query like a query engine structure. In fact, there was a guy named Andy Grove, as I mentioned before, not the Andy Grove, who founded Intel, but another Andy Grove, wrote a book about how query engines work and basically describes sort of a very classic canonical academic query engine design. So state of the art query engine design happened to be described using Scala in that particular book, but then he took that same design and implemented it in Rust. So that's what DataFusion is. And so I think actually the structure I'm going to present to you is not, I don't think, new or fundamentally like, new technology. I think it's sort of best of breed of how query engines are structured, both in the literature and in industry. If you're familiar with the Arrow project or whatever, I'm just going to briefly touch about this, what DataFusion is. So this is meant to describe the relationship between the crates and the Arrow project. So you've got the lowest level sort of Arrow crate that actually has the Arrow array formats and data types and sort of the low level computation. And you've got the Parquet file format support that's built on top of that. DataFusion sort of sits on top of both of those and adds an additional layer of stuff, which I'll talk about. And then sort of Flight is off to the side. So Paul had a blog almost a year ago probably now, that talks about sort of using these pieces. You can really, it's like a game changer to build new analytic systems, which I think it is. So anyway, this just kind of shows you where DataFusion is, right? It sits above Arrow. It's part of the Arrow repo, but it's a separate module and can be used. You can use Arrow without using DataFusion, but not the other way around. I mentioned before in passing, if you want to make DataFusion do stuff, you can pretty much add extensions to any of the pieces of it. And we've done this in IOx as well. We have our own functions, have our own aggregates. Actually, we have our own sort of specialized execution plans and table providers, right? So it's not just that the stuff is in theory could work. We've actually used it in IOx, so it's very cool to see that it works. And they use it in Ballista and they use it in CloudFuse as well, and probably other people I don't even know. So let's talk about this, right? What is a query engine? So now I'm going to start switching from like sort of sales mode of what DataFusion is, or at a high level where that fits in an ecosystem. And now I'm going to get into the guts of like what it actually is. And so to start describing DataFusion, I got to describe like the classic canonical query engine. What are the major pieces? So you've got typically it's broken up like this. If you're familiar with compilers or databases, this will all be super, it's very standard stuff. But the way a database engine is typically structured is you have a front end, which takes the SQL text, right? You get a string in that's supposedly a query, and you've got to parse that and analyze it and make sure it's referring to valid tables and all that kind of stuff. Then typically there's an intermediate representation, which is typically, people will talk about these as relational operators or a logical plan or something. And these are basically a way of describing with the data flow graph, the computation that's requested by the query. And then typically there's a bunch of optimizations and rewrites that happen on this graph. Spoiler alert, I'm going to be talking like that's exactly what DataFusion does, and I'm going to be talking about those in more detail later. And then not do you just have this sort of higher level intermediate representation, you eventually then have a concrete execution engine that actually will do the calculations and move the bytes around and bits around and whatnot. So those are the three major pieces from sort of the my mental model, and I think in most sort of classic database engines, database query engines. So obviously DataFusion's like this, and I'm going to just try to map. I'm going to be throwing around lots of terms that are now like the Rust structs if you go into the DataFusion library. So I wanted to just sort of tell you where they fit. So the front end, there's a thing called SQL statement. There's a library that actually also Andy Grove wrote for use here. That's a SQL parser. It parses SQL in the Postgres dialect. It supports other ones too. And then there's a transformation layer, which I'll talk about. Then subsequently, there's this intermediate representation, these relational operators, again, which I'll talk about later, but that's logical plan and Expr are the two major structs there, which we'll talk a lot about. And then there's the execution side. So in DataFusion, that's called execution plan, and also a sendable record batch stream, which I'll talk about in a moment. And then the data format that those execution operators are implemented in terms of is something called a record batch, which is part of Arrow, right? And that's where you hit Arrow and the actual sort of data representation. So just hopefully this is setting the stage. Now we're going to basically go dive in and go into in depth each one of these individual pieces. So at a high level, this is probably betraying some of my past life number 2 and wanting to be an architect and describe the thing at a sort of an input-output level. But like, if you're having a hard time figuring out how you'd use DataFusion, basically, if you have the input that you can describe as record batches, basically you have columns of data, and they have a schema, so that means the columns are named and the tables are named or whatever. Then you can use DataFusion to build a system where someone can give you a query, and DataFusion will actually figure out, based off the catalog information you feed it, and also the input data that it might ask, it'll produce the output also as record batches. Right, so like, if you're building a system, you want SQL support, right? Like IOx, what you can do is you can use DataFusion to do that. And yes, you have to feed into DataFusion additional information so it has enough to go, but otherwise you get full access to this support, right? There's also a secondary pattern, which we'll talk about in a little bit, which is called the data frame API. That's sort of an alternate way of describing queries that's sort of slightly more programmatic rather than declarative, that DataFusion also supports. But under the covers, it uses all the same infrastructure. So that's like, again, if you ever want to use DataFusion and you want to add, the ability to query your data, whatever it may be, this is what you can use DataFusion to do that. All right, so maybe it's all theoretic. I was kind of like seeing stuff actually work. I'm sorry, it's not a live demo, but I'll just walk through sort of what DataFusion looks like in action. So in this case, it comes with a small CLI, like a little command line prompt that'll sit there, and you can type SQL commands into it. So the first thing you can do is you can register a Parquet file. Right? So this is basically creating a table. You give it the Parquet file. Interestingly, the Parquet file has all the column information embedded in it. So you don't have to tell DataFusion what the columns are named or anything like that. It can figure it out directly from the Parquet file. And then you can just write the SQL query. So this actually was an example of something we did as part of the IOx project. Early on, we were validating DataFusion and Parquet in general. This is some of our sort of statistical data, and we were, I don't even know what it was, some subset of it. We were seeing, can we calculate the total number of different requests for this particular endpoint, this API v2 write endpoint, grouped by the status code, right? So you basically can write a query like that, and DataFusion will give you something that looks sort of like exactly what you would have expected out of a SQL database. In this case, it was whatever, right? This is all the 400 responses, so all the successful responses, or rather all the error responses, and then 200 all the successful responses. So it doesn't seem like, this is not meant to be complicated. This is supposed to be fairly straightforward. But I think now I'm going to try to take you through the journey so that by the time we end up at the end of this talk, you'll have some better idea of like all the work that DataFusion did on your behalf to actually produce that result, right? And all the really neat stuff that's going on. That's the high level, right? There's a SQL query against a Parquet file directly using DataFusion. So let's start diving down into how it actually does this. So if you're familiar with other database systems, oftentimes they include a way to get at the plan, right? We'll talk about a lot more later. But in this case, DataFusion also has that. You can say explain, whatever, and you get something that looks like this. As a crash course on how to read one of these diagrams. Yeah, I think some databases like to do it differently, but the ones I've seen typically will start at the bottom. Postgres does it this way too. You read these things from the bottom, right? So this is basically describing a tree. It's scanning a table, it's then doing a selection, which is a fancy relational algebraic name for applying a filter, and then it's aggregating. So it's grouping by status and aggregating. So there you go. There's the basic plan out of this SQL query. So that was kind of cool. DataFusion's doing that translation for you. Another way to view the same plan is, like I talked about data flow graphs, and maybe I just like pictures more than the average person, but this is a visual representation of the same plan. So again, you read it from the bottom up. You can kind of imagine, like I like to imagine data flowing through these plans, right? This is like just query engines in general, not just data fusion. So in this case, the data starts at the leaf nodes and starts flowing. So this is scanning values out of this file, sends it through a filter, which is ensuring only certain values pass, getting aggregated, and then eventually being produced. So it's a data flow graph. Data flows from the bottom to the top. That's how to think about these. All right, so I keep talking about how great DataFusion is. So far, it's probably a little underwhelming because you probably could have done the same thing in basically any database system, which is true. But now I'm going to try to peel back the cover and we'll start thinking about some of the stuff that, if you were going to write this program from scratch, which if you think about writing what would it take if you were just going to write a program that opened this Parquet file and computed this simple aggregate, right? Like did a filter and then grouped everything by a status. You could probably do that pretty straightforwardly. However, I want to start showing you this kind of stuff DataFusion does for you that you wouldn't necessarily imagine having to do, and that starts being valuable almost immediately. So if you explain verbose, you can actually get even more detail, and you can actually see there's several different logical plans that happened. So in other words, I talked earlier about a set of rewrites that occur. So you can see some of the rewrites actively happening. And here I just highlighted one thing in particular. This projection pushdown is the technical term for it, but it's just a fancy way of saying, if you look at this query, I didn't tell you, but the Parquet file has, I don't know, like 8 or 12 columns or something in it. One of the nice things about Parquet is you don't actually have to, if you only need a few of the columns, you only have to read those columns. You don't have to decompress the whole thing. It's a columnar format. And so here DataFusion knows that and actually has figured out from this query that you only need 2 columns. In this case, you only need the status, the path, right? Because you actually need this is one of the columns that you need to evaluate this predicate. But interestingly, it's not part of the grouping. So this is just trying to show that DataFusion actually figured that out and already pushed it down for you. So already sort of, even with the simplest of queries, DataFusion saving a bunch of work, right? That again, smart programmers, you could figure that out, but it's, you don't have to if you're using DataFusion. All right, so before we delve into more depth about, again, how this underlying query engine is happening, and again, it's only getting deeper from here, so I'm sorry if I'm going too much in detail, but I've got a lot to get through, not a super amount of time. So I need to talk a little about record batches, which I've been throwing around as a term without really explaining what they are. And this is part of Arrow, but I think you kind of need to understand what's going on here to appreciate more of what DataFusion is doing. So I just wanted to give an example of sort of this textual representation of a table. When I say record batch, what that actually means. So Arrow, if you're familiar with it, in Parquet actually as well, but what's important is Arrow here is a columnar-based format. And so practically speaking, what that means is you don't get like one row after another. What you get is you get subsets of the columns. So in this case, we would have, you might represent this data as 2 distinct record batches. I just picked that, it could be whatever, it could be 1, it could be more. With 4 rows, it doesn't matter at all, but with like 4 million rows, it probably matters that you broke it up into chunks. In this case, each one of the record batches has the same number of columns. So it has 2 columns because that's what the thing, those are individual arrays. In this case, there's a string array and a uint64 array. It's actually probably called UTF-8 array, but whatever. And there's a bunch of details about making this efficient and performant or whatever that as part of the Arrow library. Likewise, the second record batch would have 2 arrays, 1 for each column, same types, and just the next selection of rows. So these are record batches. This is important because I'll talk about later that DataFusion is a vectorized execution engine, or you might see that term floating around in either marketing literature or technical papers. And it just means it works on, it doesn't just work row at a time, it works on a batch of rows at a time. And so the specific implementation of that in DataFusion and Arrow in general is this record batch. So record batch is this vector of things. And it also has a schema, which basically just gives the names to the columns. That's all it does. And that schema is the same across different record batches, which I tried to show with this shared Arrow. So yeah, so this is, I don't worry too much about that. Just know that it's important that they're columnar. So let's dive into query planning. So now I'm going to walk through the three different phases, right? You get the creation of a plan from the query, then we'll go through the various optimization phases that happen on those logical plans, and then actually how it goes off and gets executed. So at a high level, super high level flow is you get the SQL query, you go through this parsing phase I'm describing, which is you get this logical plan, right, which I talked about. It's classic query optimizer stuff, or classic query engine stuff. Postgres would call it, by the way, Postgres calls that a query tree. Other databases I've worked at would call this the query plan. So this is the thing that like the database query optimizer works on mostly, right? So there's a bunch of optimization passes that happen on the logical plan, and eventually that will be compiled or transformed or transpiled or whatever the current hipster way of describing transforming one data structure to another is, into what DataFusion calls an execution plan. Postgres calls as a plan tree. Other terms you'll see in the literature like access plan or an operator tree or all that sort of stuff. Typically, most database systems actually these are different because the logical plan is a higher level concept, and there's lower level stuff that happens in an execution plan, which actually I'll try to give some illustrations of that later. And then eventually you run this thing, you get record patches. So that's like the super high level flow. So let's go into each one of those in detail. So the logical plan creation, as you might know if you've ever worked with SQL, it's declarative. So that basically says, you tell the system what you want, and then the value of the database system is that it goes and figures out how to do that most efficiently. So that's the classic SQL declarative input. If you've ever worked with SQL, you either love it or you hate it. But if you're in the hating camp, like you oftentimes people will want another way, not just tell me what you want, but I want to have more control over how you get it. And so I would call that sort of procedural or basically not declarative. DataFusion conveniently supports both these models. It obviously supports SQL, which I've been talking about, but it also supports directly building up these logical plans and running them. So there's two different ways to do that. One, there's a sort of Rust style builder called Logical Plan Builder, which you literally build up the different stages of the things of logical plans. And the other option is you can use a more data framed API, which if you're familiar with Pandas or Spark or have used those, I think that model has become very, very popular with people who are sort of doing data manipulation or processing. And under the covers, that actually builds logical plans and runs them through all the same machinery I'm going to talk about. It's just a different sort of programming interface provided. So DataFusion is both ways. So the way SQL gets to a logical plan is, like I mentioned, it goes through a SQL parser, which shouldn't shock anyone, but that takes a text string like this and turns it into a tree, make sure it's well formed. And then there's a pretty mechanical translation step, which again, like it's important. I don't want to trivialize this. It was cool code to write. I didn't write it, but who wrote it, like it's cool code, but it's pretty mechanical, and it just it's called the planner, and it turns it into a logical plan. Then there's also this data frame API, which I rewrote the same query, right? This select thing that's grouping by status and filtering. I wrote that in terms of the data frame API. So this is what to build get the same answers. This is how you would use the data frame API. So in this case, it's sort of very procedural. Right? You tell this thing, I want to read this table, then I want to filter, and actually this is the sort of some Rust functions that build up an expression tree for you. And then I want to aggregate it. You tell it what the aggregate columns are. So I want to group it by, or the grouping column. So I want to group it by status. And then there's the aggregate function, count by count of one, right? Count star, whatever you want. And then there's a structure in there called data frame, and that also spits out a logical plan. I'm pointing this out because even though, I think it's a good example, DataFusion has a couple of different front ends, right? You can use data frames, you can use SQL. IOx, actually, we're building a front end that generates, this is how it connects to the existing storage API, right? So we effectively have a front end so that when the rest of the Influx ecosystem wants to query data, right? We also now have our own sort of system which builds these logical plans and then takes advantage of DataFusion from here on in. So once you have a logical plan, here's some stuff that if you want to know what possible nodes can go in that logical plan, here's the list. When I did these slides a week or two ago, these stayed fairly simple, but they've got all the major things you would expect in a plan. So you've got the join. Join is a big one. That's still a lot of work to do there, but it's got table scan. It's got ways to repartition the data and aggregate it and filter it and limit it and all the good stuff. And there's the extension one, so you can plug in your own operators to these trees, which again, actually we do in IOx. Maybe I should talk about that sometime. But so yeah, but this talk's already going to be full enough. I'm not going to go into detail on it in all of these different types. Instead, I'm going to move on to the next part of the query optimization pass, or the next part of query planning, which is query optimization. There's like a whole body of research literature about all sorts of various optimizations you might or might not do. However, they all pretty much have the same like high level structure, which is you take a logical plan, you run it through an optimizer pass, and effectively do a rewrite on it. And the goal of this optimizer pass is that the output computes the same results, hopefully the same correct results, only faster through various different ways. So that's why it's called optimizing, right? Because it's optimizing how to actually calculate the same value. So that's what those do. So let's talk about the different optimizer paths that DataFusion has, which actually, I think there's a pretty good list. Like these are if you were going to write a query operator, these are the ones that you need basically immediately to have any sort of reasonable performance. So the first one I already demonstrated earlier, which was projection pushdown. So that's a fancy database term for saying we're just going to only pass the columns up through the plan that we actually use, right? Like it's that simple. However, you've got to actually do the calculation of what columns does this use, where is it used in the plan. If you look carefully at the query I showed, it actually needs to bring a column out to, even though there's a column that needs to be scanned from the Parquet file that doesn't actually appear in the select list, right? So the final outputs only have the status and the counts of them, but however, you actually need to scan an additional column in there so you can apply the filter. Which, it sounds obvious, but in more complicated query plans, making sure you don't overscan stuff is, non-trivial to do. It's also got classic predicate pushdown or filter pushdown, which effectively, because as I described those data flow graphs, the plans are really about you suck all the data off disk or wherever they're coming from, and you run through a bunch of operations and produce results. Right? So if you can avoid passing data through those intermediate plans by pushing filtering down lower, you can. So that's like another classic. Like you've got to have that to have any reasonable performance. Hash probe build order is a fancy way of saying join reordering, which I won't geek out too much here. I spent a significant chunk of my time at Vertica working on this, but at the end of the day, basically, different join algorithms with different properties of the inputs aren't the same, and so making sure you order the joins in the right way can make a huge difference in performance. So DataFusion has a basic version of that, and then we also have constant folding, which is the way of saying partially evaluating expression. So the example I have is not super compelling, right? If you've got column A and true, you shouldn't bother to do that and true. You should just return column A. However, there's more interesting ones that are probably more relevant, like extract month from a constant timestamp, right? That's very convenient to write, but if you implement a naive execution evaluator, you'll end up effectively doing that calculation for every input row, which is super inefficient. So anyway, those are cool stuff. Let's move on to the next. So speaking of expression evaluation, let's talk about that, because I think depending on where you're coming from, this might or might not be obvious, but this is something that DataFusion really adds in addition to Arrow, right? Like, and if you're coming to Arrow and you want to do something with your data in Arrow arrays, you might find it overly cumbersome without something like this expression. So if you look at the way Arrow is set up, I'm talking about the Rust library now, but the C++ library is very similar, is it's composed of compute kernels. So if you have two arrays, you can, or if you have an array or two arrays, there's lots of little operations you can do on them. Like maybe you can compare them for equality, or you can check whether or not one's greater than or less than the other. But however, since Arrow is strongly typed, there's a whole bunch of sort of very specific implementations that you'll find in the Rust implementation. For example, the strings are treated differently because the types are different. So you have, if you have certain kinds of arrays, you call one kernel. If you have arrays that have string values, you have to call another kernel, which, it's not the end of the world. It's just kind of it's a lot of bookkeeping to keep, right? So instead, if you're using DataFusion, DataFusion has a higher level expression language that you can use to get to basically call the right kernel without having to worry about the details. So let's take an example of this expression, maybe not the most interesting one, but I think it will illustrate the point. So like, let's say I wanted to find all the, I'm still doing the same query, but instead of just checking for this columns equal to that value, I also want to see if it's null. Right, so I have two conditions. Here is the corresponding, if you want to build that expression using the expression builder API, which might or might not be interesting to anyone, but I just thought I'd throw it in there. So the way DataFusion handles this, again, like this is a more complicated predicate than just a simple single column equals something else, right? It can be an arbitrary expression in here. In this case, it's represented as an expression tree. If you have ever taken a compiler's course or database course, if you've ever done an expression evaluator, this will be very similar to you, or should be familiar to you, but I'll just walk through it quickly if it's not. So if you look at the structure of this expression, you've effectively got path equals some constant, right? So that's expressed down here in this tree. So this is the binary Expr. It's a fancy way of saying some operation that takes two inputs. It's got a column reference, a path, right? That's that part. It's got a literal value, which is the string constant that's there, and it's connected by inequality. On this side, you've got something similar. You said path is null. That actually happens to have a special representation. You're not comparing it to a constant null. There's a special way of checking for nulls, but so this right-hand side looks a little different, but it's still, here's the column reference. And then they're combined with a binary expression that says if either the left or the right is true, then the output is true. So a lot's going on here, actually. There's different data types that are flowing, right? Like column path in this example is UTF-8, so it's a string. The output of this thing is actually binary, true or false, Boolean. So, it's some non-trivial stuff maybe going on here, even if it's fairly simple. And so what I'm going to do now is I'm just going to walk through like how DataFusion evaluates this using the arrow kernels, just in case any, to give you, just to show you how it works. So here's the tree, and I'm just going to walk through and show how the data flows through this thing. So it's a pretty standard interpretation. Like if you're going to write an expression interpreter, it would look something like this. So however, DataFusion is vectorized. So the first thing that happens, which means you operate on vectors at a time. So the first thing that happens is you get the input array comes in. Let's say that's the values of the column path. Then you get this literal, which is just some constant in memory somewhere. Then DataFusion knows enough to call the specialized kernel that says, given this array of strings and this particular constant, right, figure out which one of the entries in the string array are true. So that effectively produces a new arrow array that has type Boolean. It's actually bit representation, right? And it's got its own specific data type. Now, the same thing will happen on the other side. So you get the same input values again. So this time, because of how arrow is structured, you don't actually copy that. You don't have a separate copy of the data. It's actually the same underlying copy, but logically speaking, it's another copy of the data. You evaluate the is null. There's a special is null kernel on it that also is sort of optimized for arrow. You get a second array here showing all the values that were null. In this case, there were none, but I just had to make something. And then there's a specialized kernel that takes two Boolean arrays and ORs them together. And so then that gets invoked and you eventually get your final output array. So that's sort of how expression evaluation proceeds. And again, like unless you're working like implementing DataFusion, you don't have to understand that, but I think it's cool to see that DataFusion has that functionality built in. So you don't have to implement that if you want more sophistication. Other stuff that's important to implement if you're actually implementing a query engine that might not be obvious when you start, but you'll really miss it when you don't have it, is like, let's take something like square root of a column, and let's say that column is an integer of some type, maybe 8 bytes, because that was efficient to store it or whatever. But it turns out actually square root typically only has implementations for 32-bit or 64-bit floating values. So if you're writing this program, you know that you'll have to cast call to one of those other types before you could call square root. But if you're writing a query expression evaluator, now that logic to know whether or not you have the right data types to call what function and doing something about it if you don't, it's called type coercion. So, again, this is just something cool that DataFusion has that doesn't seem hard, and well, I don't know, it depends on what you're thinking. The point is, you don't have to write this, right? So if you're interested in this, you can, but DataFusion just has it, and this is like sort of table stakes for actually implementing it. SQL for sure, but also sort of any kind of expression system with non-trivial types. So in this case, DataFusion will automatically add a cast to automatically switch this column to float 32 and call the appropriate arrow kernel. And there is an arrow compute kernel that will do that for you. But you didn't, hopefully as a query, this is one of the things that like why people like query declarative queries is you just say what you want and you let the system go worry about the details like this. And of course, there's other, like I keep saying, there's other stuff you have to worry about here. Like you don't necessarily want to cast like 128-bit floating point down to a 64-bit floating point because you might lose precision. So there's a bunch of rules about coercion of when you can and can't do them and whether or not they can lose data or not. Again, DataFusion has this, and it's pretty cool. So, all right, let's move on. If you guys don't mind, I think we only got 10 minutes left. Maybe I can get through here. Is execution plans. So this, I will admit, if I was trying to, I struggled to explain internally to some of the IOx team how execution actually worked in DataFusion because it's got it's like got async going on, there's multi-threaded and a whole bunch of stuff. So I tried to do it here. Hopefully it makes sense. So this is what I originally started with. How do you talk about DataFusion execution engine? It's got a bunch of these features, right? It's async, it's vectorized. That's a fancy way of saying it just does record batches at a time rather than one row at a time. There's some other sort of terms I tried to apply to it that might be interesting if we ever write an academic paper about DataFusion, but I think what's more interesting is we'll just go through an example of how it actually works. I think one of the more interesting things is that it uses the same thread pool as the standard. It uses the same standard thread pool as asynchronous work in Rust does, which is called Tokyo. That's still, I would say, I would say there's still some open questions and unease about whether or not we need another thread pool or if there's more better scheduling techniques that we could apply. But this is how it currently works as of this weekend. So plan execution proceeds in the following manner. Logical plan is translated directly to execution plan. I have an example of this later, so don't worry about too many details. You take a logical plan, you convert it to the execution plan. That execution plan, then there's a function called execute on it, which will turn it into what is called in the Rust code sendable record batch stream, which is a fancy way. What that is it's basically an iterator. So if you're from Python, it's like a generator, so it means it doesn't produce values until you ask for it. So it's got some functions like give me the next value, give me the next value. In this case, it happens to also be async. So what that means is that you say give me the next value, and the next value might or might not be there. And if it's not there, you'll wait for it basically, but it will do so in a way that doesn't block a thread. And then eventually you can call collect on the record batch stream, where you can sit there and pull next on it yourself, and you get the output of the query as record batches. So that's like the high level sort of flow. And I'm going to now go through the process of taking my same query as before, and we're just going to, I tried to walk through what actually happens, and maybe I think this will be instructive. So the first thing that happens is it takes this physical plan and it turns it into an execution plan. So in this case, we have a table scan of this thing. At a high level, it's just reading some table that has some columns. By the time it gets an execution plan, now we know it's coming from a Parquet file. In particular, it had two distinct files, maybe, which we'll call partitions. I'll talk about those in a second. Then there's a filter exec, right? So this is the filter struct that actually implements filtering. Also has two outputs because it's had two outputs, output partitions. Now we have a hash aggregate. So that's the thing that's computing this logical aggregate operation. There's actually multiple different potential algorithms to implement that. DataFusion implements something called hash aggregation, but there's also sort-based and merge-based, and probably some other fancy stuff too. But anyway, so at this point, we've picked a particular algorithm. Here you can see it's grouping by status, counting on one. Interestingly, something that didn't appear in the original logical plan, but shows up in the execution plan is another two operations. So in particular, what this is DataFusion trying to parallelize the plan for you across cores. And so if you're familiar with MapReduce or something else like that, this is like a pretty classic two-stage aggregation. So what's happening is the first stage, it's called the partial aggregation. This is basically happening in parallel on a couple of different streams. In this case, 2 different files, or maybe 2 different record batches within those files. Can happen in parallel, don't have to talk to each other. And then eventually you have to merge those 2 streams of partial aggregates back together and do a final calculation. And so you can actually see here's interestingly, right, this final actually uses sum rather than count, because the way, if you basically count all the groups in the individual partitions, the way you combine those groups is you can't just count the counts, right? That would be wrong. You have to sum the different counts. So, and this is basically like the classic, if you look at the MapReduce paper, right, like this is like one of the classic examples of using like the map phase and the reduce phase. So sorry, I'm just trying to say this is not like anything unique to DataFusion. However, the fact that DataFusion does this already for you, you don't have to worry about this, is one of the ways it gets good performance. So you take this plan. Now I got an execution point. Now I'm going to actually call execute on it, which is going to prepare and actually get things ready to rock. So in this case, it makes sense. Which then is merged. You get an equivalent stream for merge. Then interestingly, because merge had 2 inputs, you build 1 copy of these things for the first file in my example, and then you also build a second copy for the second input. So hopefully that makes sense. So you basically have 2 things that are going to be running in parallel. You can actually see them operating in parallel. And if there were like a bunch of different record files, Parquet files, you would actually run them all in parallel eventually. So that's the high level. So what happens is as rows come in here, this thing merges them together from both inputs and sends them to the output. All right, so now you have this thing, and now I keep talking about multi-cores and how it's going to run in parallel and all that kind of stuff. I'm now going to try to walk you through with the diagram how that actually happens, and hopefully it will make sense. And if not, I'm sorry, but we're almost out of time anyway. So the way I'm going to do it is I can't fit it all on one slide. So I'm going to do the top part. I'm going to do this bottom part first, and then I'll talk about the top part and put them together. So the way the bottom part proceeds, we'll see why this is good in a second, is that I have a handle of this thing. I'm ready to make values. And actually, before I do anything to this, in the background, a task is spawned. That's Rust async IO speak for possibly a thread, right? So it might run a different thread, it might also run on your same thread, but basically it could run asynchronously. And that task immediately calls next, and then it immediately calls next. So it tries to get input from the filter. The filter to get input to produce any output needs to get input from the file, and so it calls that. If you're at all familiar with execution engines, this part that I just described is a classic pull model, right? So you actually get the rows here, you'll process them here, and you'll return the results as part of the same sort of call chain. That's what's called a classic pull execution style, and it has nice cache properties because the same values are being used by the same core typically. So anyway, eventually what will happen is this Parquet stream will be done. We'll return the file, return the data from the file, some data from the file as a record batch. At that point, this call returns filter exec, filters the data in hash aggregate, finally gets the data, and it feeds it in and builds it some hash table. And that process will then proceed until the input Parquet is completely read. Then the hash aggregate is ready to produce an output, and it generates a record batch that has the contents of the hash table. And then at some point along the line, output's going to be requested. I'll show you where this connects in a second. And when that output's requested, if this record batch up here is ready, it'll just get returned immediately. And if not, this task will effectively wait until it is ready. And so eventually it gets returned to the caller. So that's already kind of crazy, right? This is basically doing some pull evaluation, but happened yearly because it was running on its own task. Now, we look at the top part of the plan. Remember, this is the top part that's going on. This was the top of the previous slide, right? That's this piece. So now I'm going to show what happens at the actual overall plan. So again, before anything's asked of the actual plan, DataFusion will go off and spawn 3 distinct tasks. The first to pull data for the input of this group hash, just like in the last slide. And then also MergeStream will also launch independent tasks to pull inputs from each, to basically pull at least one input from each one of its inputs, to pull one record batch. And it's set up with channels so that it doesn't, it doesn't, effectively has back pressure too. So these queues are set up so that it only has one ready to go, and it won't start computing the next one until until the first one's computed or is actually produced. But anyway, so now we effectively have potentially 3 threads here if there's enough threads going. And what will happen is, the group hash one will call MergeStream, give me the next thing. That's probably not ready immediately, but and the other 2 tasks will immediately call next on the group hash. Then the process that we just showed in the previous slide will happen. So a whole bunch of record batches will eventually be produced as the output of the hash tables. But again, like they happen on some different thread potentially, or maybe the same one depending. But the Tokyo task thread pool is handling that. And at some point, oh yeah, in this case, I'm going to just say, oh, by the way, the output gets requested at this point. There's no output ready, so it just waits. So at some point, the output from the previous slide will get produced. That will then get fed into the merge stream. Merge stream, despite its name, actually doesn't look at the data. It literally just passes the blocks from its inputs to its outputs. But it's just called merge. Like before, the data that's coming out of merge gets passed into this final group hash aggregate that computes the final sums. That produces the record batch, and that record batch eventually gets produced, returned to the caller. So I think I'm basically out of time. Thank you very much for listening to that. Hopefully that was interesting. There's all sorts of stuff going on online if you want to check us out. But that's pretty much it.
Awesome. Thank you, Andrew. So we do have questions. I know we're out of time, but we will still take a couple questions if they do come in. Let's see. How does IOx differ from SQL? This could this not be something that PostSQL could do also in the background with DataFusion? Or is it that with DataFusion and Parquet files, you can use blob storage, or is it some other hidden optimization for time series data?
Yes, I don't know, Andrew, if you want to field that in the context.
Yeah,
of
maybe I'll just
Fusion,
feel
but
like, I'll talk about the DataFusion part, then you talk about the main part. Yeah, so yeah. Like I tried to describe before, DataFusion fits this like very specific piece of the database, right? This query engine, and it's got all these hooks, right? So IOx has the time series specific optimizations for all the other layers. And then also where we've hooked into DataFusion, there's a bunch of time series specific stuff as well.
Perfect.
Yeah, and from an IOx perspective, I mean, even from the DataFusion perspective, like one of the goals, one of the dreams is like, it's columnar execution engines who ideally for the kinds of queries that you have in time series data, like windowed aggregates and all this kind of other stuff, it's hopefully the goal is it's going to be faster. Yeah, and the other thing, which is like Postgres's entire like database system. Now, IOx obviously aims to be a database system, but it aims to be a database system in a very narrow, kind of very specific scope, right? We don't want transactional workloads where you're keeping reference data. It's basically all about time series data, event data, and stuff that you have coming in. And ideally, like data.
Just a quick intro, we can. If we have any items that we want to discuss.
Oh, Andrew, can you?
So yes, I think I'll say hi. I'm
sorry. I'm double booked.
So, yeah, no worries. So yeah, that is one of the big parts is using object storage with Parquet as the backend store, right? So basically like achieving much better data compression for the data that's at rest, having an automated system that will manage the life cycle of here's the hot data you're querying to pushing it off to object storage and then reloading it from object storage when you need it. And then the other bit of this is even with the in-memory query execution, right? There are these two sides that IOx has, which is one is the mutable buffer where data is landing for writes, but the other is the read buffer where again, it's optimized to have the data in a compressed format in memory. And it's optimized for query execution for the specific kind of things we're trying to do, right? So we want to be able to do like, billions of records per, or billions of, values per core within the database and compute answers on larger sets of data. And again, all of this is predicated on the idea that you have large blocks of data within your database that become basically at rest. They can be compressed and they can be optimized because you don't have to worry about updates to those records. We certainly will have tools to do that, but those aren't necessarily going to be like cheap operations and operations that we expect to have happen all the time. It's kind of a different kind of use case generally. So.
Awesome. We'll stay online here for another moment in case anyone else has any questions. I just threw in the chat the registration link for the April session of InfluxDB IOx Tech Talk. So, we have these sessions every month. So we are super excited to hear from you guys. Do you plan on harnessing Linux's send file?
So I'm not super familiar with this tool, but I assume you're asking that in relation to sending data back and forth, like actual files back and forth. I could be wrong. Essentially, what we want is we want object storage to be persistence, the persistence layer, and the local file system to essentially be a cache of the things that we need to work with. So I'm not sure what the context is for that question, and unfortunately I'm not familiar with send files. So
Boaz, I just allowed you to talk. If you want to add any clarification to your question, you should be able to unmute yourself and talk to Paul directly.
Hi.
Hello.
So Linux send file allows to write from one buffer to another, to read from one buffer and write to another buffer without leaving the kernel space. So my question is whether IOx is planning on using like this raw data that comes from an HTTP stream or TCP stream and write it directly to the wall, like the same way Kafka does it. But his answer was quite...
Yeah. So the thing is, like, as the data, at least for the formats we support right now, the data has to be parsed, it has to be validated, right? It's not like Kafka where it's basically just a raw byte stream that you can move. Now, wherever we can, we are going to try and implement zero copy semantics in terms of moving that data around. But there are definitely points in the system where data gets translated from one format to another. So this leads into a question that I see in the Q&A, which is the mutable buffer based on Arrow? And the answer is right now, no, it is not. Like the internal format of the mutable buffer is basically like raw Rust structs and stuff like that. And when it gets queried, it gets translated into Arrow record batches. But as another example, the read buffer is not actually Arrow record batches either. And again, that's because we want to achieve compression. Arrow has some different requirements in terms of what it's trying to achieve. And the problem is one of those things is O of 1 access or constant time access to any individual member. And depending on what compression scheme you use, you may not be able to get that. And with the read buffer, we're trying to balance compression with query performance and stuff like that. And now it just so happens that Arrow record batches are essentially the standard by which data moves from one to the other. So from the read buffer to the query engine, from the mutable buffer to the query engine, and then also from the query engine out to clients that are requesting data if they're using Apache Arrow Flight. So there's definitely some improvements that we can make there.
Awesome. Thank you, Paul. Cool. Well, once again, if anyone has any last minute questions for any of the panels, please feel free to post them in the Q&A box. Once again, another friendly reminder, we have Influx Days EMEA coming up in May. So we look forward to seeing our fantastic community there hanging out with us as well. So really appreciate you guys staying on today. I know we went over a little bit, but it seems like everyone was enjoying it. So
Thanks, everybody.
Thank you, and hope to see you guys all next month.